Okay, so we will see the shear effects on the members today. So this basically similar to what we have been looking at for axial and bending. So you can see here the shear effect is taken into account by 60% of the yield. This is in contradiction to tubular members or API code. We were looking at 60%, not 60%, is 40% only. So that's one major difference, but of course it will be adjusted by means of other load factors. So you see here 60% of yield multiplied by the area of web, that is the allowable or nominal shear strength of the web or the member in question. If it is a horizontal, then you will be replacing this AW by the area of the flange, because it is a vertical shear, you will take the capacity of the web, whereas a horizontal shear you will take the two flanges, top and bottom flanges area for the AW. That is what I have just written here in there, and multiplied by a coefficient called a CV, which is basically a shear buckling coefficient, which needs to be calculated depending on the parameters such as the depth and the thickness of the web. And from the nominal capacity you can either calculate the design capacity or allowable capacity by doing same dividing by a factor of safety or a material factor. If it is a LRFD design, you multiply by 5, which is your material factor, or you divide by the factor of safety, which is conventionally 1.67 for almost all of the cases. Remember, we were having axial compression and bending 1.67, here you have 1.5. So if you divide 0.6 by 1.5 will become how much? 0.6 divided by 0. So automatically, so that is how the adjustment has been done. If you look at API, we were having allowable shear capacity is 0.4 times Fy. So here the load factors have been adjusted accordingly. So the unity check is again similar, shear load divided by shear capacity will give you the unity check for shear, and load factor multiplied by shear load divided by the design shear strength will give you the unity check. So the adjustment is only on the multiplication factors for LRFD, division factor for allowable strength. And I will repeat again, for minor axis bending, AW will be replaced by the area of the flanges. So vertical shear is only the taken by the web, horizontal shear taken by flanges. This is in similar explanation what we were having for circular sections. You know, the area of for shear is taken as 50% by simply, if you just make it as a square. So there will be two flanges, two webs. So 50% for vertical and 50% for shear. Of course, you can integrate and get it. So the shear strength is very easy to calculate. Basically, what you need to know is the area of shear, whether it is horizontal or vertical. Now this shear buckling coefficient CV needs to be calculated. Here we have got two cases, webs of I-shaped members or webs of fabricated sections. I think we have seen earlier, you know, how the fabricated sections are made by taking flat plates and then making a fillet weld or full penetration weld. So there is a slight modification to the CV. As long as you buy a I-shaped members, CV value is 1.0, whereas for fabricated sections where you make it cylinder, you know, the idea is the height of the web to the thickness of the web is becoming higher, then you have a cylinderness effect. So local buckling may govern instead of 60% of yield, which is basically taken as a shear capacity. So that is why we have got three cases, when H by TW, which is simply the cylinderness of the web, is less than 1.1 times this parameter, which is basically the new one coming in here is a kV times E divided by Fy. kV is defined as a coefficient associated with spacing of stiffness. So remember, if I draw one plate girder, we will just and that is your support, and your web is stiffened by stiffness in this fashion. So that is your, so periodically you provide stiffness. So what it means, we made the web too cylinder, that means thickness is too small, So, we have two choices, either to increase the thickness of the web to make it stronger enough so that the buckling does not happen, or we go and provide perpendicular so many stiffeners that the web will not wobble around. So, but you are spending some amount of extra steel, without which you are not going to get, because as soon as you do not have the stiffeners, Kv value will change and corresponding Cv value will be less than 1, makes the allowable stress smaller. So, either way you are not going to get the shear strength freely by just making cylinder, making bigger and bigger, you are not going to get the capacity. So, that is exactly the idea. So, H by Tw is less than 1.1 times this parameter, Cv is 1, that means it will be treated same as the rolled shapes, because the rolled shapes, remember yesterday I was talking about all the rolled shapes from either American code or from Indian codes, they purposely made it as compact members with compact flanges and compact web. So, only the fabricated girders, we try to manipulate the moment of inertia by simply making the web higher, and that is where the problem. So, the second case will be between 1.1 and 1.37, Cv value is calculated using this, and if it is greater than 1.37, then the Cv value is calculated using this empirical formula. These are empirical formulas relating the shear capacity and the slenderness. Now, A is basically the webs with stiffness spaced at a distance A, which I have marked on the drawing here. So, the spacing is denoted as A. As long as A is higher, then the Kv value will be smaller. Once the Kv value is smaller, Cv value will be also smaller. So, basically the larger the spacing is no good, closer the spacing you are going to get a better stiffening. So, that is the idea behind how shear can be enhanced by providing additional stiffener effects, or you just make it thicker. You know, if you make it thicker, you will anyway come under the category of 1, which will automatically make the CBS 1, and then automatically you will go back and you calculate the nominal shear capacity with the area times 0.6 Fy as Cv is equal to 1. So, shear capacity calculation is quite simple, in a way it is not complicated as bending, and once you know the loading, you can go back and calculate the unity check, the load divided by capacity. Here load multiplied by the load factor divided by design capacity. A simple diagram, just I have plotted these three equations, part 1, part 2, part 3, just to understand how the web slenderness affects you know, the Cv coefficient. Cv is 1, where the web slenderness is very low, I think around 80, and then after that it becomes drastically reducing. As you can see here, almost with 100 you are able to reduce the capacity by 50%, not very good, you know. So, that is exactly the idea. So, we need to keep the slenderness less than 60, 70, so that yesterday we were seeing web slenderness is the limit was 90, you know. If you look at the compression elements, is 90 is the web slenderness, otherwise it will start buckling, basically it will be wobbling around. So, this is the idea behind. The next one, we have already calculated the axial capacity, and then in tension and compression, and bending capacity in minor axis and major axis bending, and also shear. Now, there will be load cases where you will have concurrent existence of all the loads together in any beam or column. So, what we need to see is similar like API codes, we need to see the possibility of combining them, so that the beam is safe in coexistence of all the loads. Until the 9th edition, the unity check or the interaction equation is very similar to API. In fact, from AAC the API was developed, but in the recent times, due to change in you know, several data obtained from experiments, AAC has come up with a slightly modified equation, but of course, the fundamental principle of linear superposition still not changed. So, you can see here is almost similar, except instead of stresses you see here is a capacities, very similar to what we have learned from our joint design in API, isn't it? API also will be very similar, but of course, API does use the non-linear interaction instead of linear, but in here is typically you will see a linear summation of the axial and the bending effects. but what difference it makes? One thing we have made in 14th edition, that the P delta and P delta effects have been taken into account by a slightly different means. There are three options given to you. One was trying to do the correct second order analysis, incorporating P delta effects and P delta effects. Second option was to use only the effective length factors in place of second order analysis, which is difficult to do. The third option was to calculate the effects of P delta by means of an empirical coefficient from the derived moments and the displacements obtained from first order analysis. Now, any one of these method you can use, but 14th edition. So, if you use method 1 and 3, not the effective length method, then you will be using the moments modified by these effects. That means, already incorporating those two effects, the moments and the axial forces are recalculated. I think yesterday we spent some time looking at the moment obtained from first order multiplied by beta 1 and beta 2, you get a value which incorporates those effects. So, that is why you see here, if you just recollect the equations that we have used for tubular members, you will be seeing something like this. Let me just quickly go here. I think you might see these effects. So, what is that bottom term? In fact, if you look at this is axial stress by axial allowable stress, which is nothing but axial load divided by axial allowable load, and the second term is bending stress divided by bending allowable stress is here. But what is the extra term here is basically that P delta effect. As long as you have a larger deformation effects, you will see that the axial stress is more, automatically corresponding buckling stress will be less or more depending on the loads, and this parameter in bracket will always be reducing the allowable stress for bending. So, this is basically taken as an indirect means of, you can derive this, the interaction whatever we are having is can be derived, and this parameter will always be the more the axial stress, that means the reduction factor will be smaller. Once that factor is smaller, it is indirectly reducing the amount of allowable bending stress that you can allow. That is the idea behind it. So, that is taken into account in API, whereas instead of taking into account it here, we remove this, but automatically we have already taken the additional moment because of the P delta effects in the nominator instead of denominator. So, that is a slightly different form, but of course, the fact is the moments are magnified here, whereas the allowable stresses are reduced here. It is going to produce exactly the same result. So, that is the difference that we wanted to highlight, that you should be using slightly different form of checking instead of API, you will be using here as simple form. And again here we got two subclasses. One is when the load is axial predominant, then you have got this formula. When axial is slightly smaller, less than 20%, then you can use the second segment. Similarly, like we had in API, when the FA by FA is less than 0.15, you got a set of formula which is slightly modified, and when the predominantly axial stress, then you have a interaction formula, something like this. This is for the buckling case. So, basically this will give you an idea that why this form is different, because we have incorporated the magnified moments and magnified forces from second order effects in the denominator. So, there is no downgrade effects on the allowable bending moments. So, that is the idea behind. Of course, this is for doubly symmetric sections, but then for the unsymmetric sections, AAC does ask us to use this type of equation similar to what we have been having in API. One of the equation is like this, of the 4, one of them is this way, but of course, in here we are going to use FBX after magnifying the moment because of the second order effects. That is the only difference, whereas in API you do not do that, you actually use the nominal stress applied, and basically that difference. And the stresses are calculated in the following manner: FB and FA are applied stresses which will be calculated from the moments obtained from the second order or the first order analysis with the factors multiplied by B1 and B2, and the allowable stresses are obtained by the capacities that you have derived so far divided by the either the factor of safety, or in case of moment you divide by the section modulus which you have already derived. So, if you substitute back, you will get back this equation, the first equation, you know. So, that is the difference that we are trying to make, only the 8 by 9 is missing. So, unsymmetric sections you can use this, for symmetric sections you can use this. I have just plotted a typical graph of interaction diagram between the axial and so instead of non-linear we used to see in the tubular connections, it is a linear 2 segment curve, you know, the denoting segment 1 and segment 2. So, that is the idea behind, you can plot this. One of them is the ultimate, the other one is allowable. The second one is nominal, this is the ultimate, just divided by the factor. So, unsymmetric sections, as you can see here, the factor of safety against compression and bending is 1.67. Sx Sy is the elastic modulus, which I think you should know how to calculate. So, having done all this, why I wanted to highlight here, this was what actually originally proposed in the 9th edition. You will even see now API and this AAC old edition is matching. In fact, the same equation is copied in API RP2A for tubular sections, and the difference is only P delta effect is taken, whereas the P delta effect of the sway frame has not been taken. That is because most of the offshore structures, especially jackets, we always have braces. That is why it has been taken indirectly. So, if you have an unbraced frame, then you will have a sway, whereas most of the jacket structures what we are designing will actually put considerable amount of bracing, and that was why if you read API carefully, everywhere you will see that portal frames, the indirect means of taking into account this P delta effect is by applying larger effective length factor. If you just read carefully the table in the API, you will see that the portal frame effects are taken by increasing the effective length factor by 1.2, 1.4, something like this. So, that the allowable stress automatically comes down. So, there are several indirect ways of dealing with it, but the best way of doing is simply do a proper bracing, so that the sway effects are reduced to considerable extent. This is the diagram that I have just taken from AAC for both LRFD and ASD, just to give you an idea that you may have the axial force either tension or compression. So, that is the idea behind. So, you see here this is compression, the negative value means is tension, just a mirror image of the graph what I have just shown here, this you will see on the other side. So, mostly you might have seen such an interaction diagram for concrete design in concrete design course, either AAC or British course or IS 456. Again the difference is here you divide by the factor safety factor, which is 1.67, here you multiply by the material factor phi. So, with that I think the design of open sections, which is specifically for I section, we have covered axial, compression, tension, bending, minor axis, major axis, shear and the combination. I have just taken a typical example problem for you to just practice in case. So, in this example I have just picked up a simple plate girder, fabricated girder of these dimensions. The height of the beam is 1000, flange is 500 and web is 20 mm thick, flange is 30 mm thick, and just ask you to design in accordance with the 14th edition using allowable stress method. We have now the idea of how the LRFD also works. In parallel we have worked out, most of the equations are given to you, basically the difference is only in the capacity calculation and unity check, remaining whether it is the buckling calculations or the allowable stress calculations or allowable capacity calculations, every one of them is almost similar. So, that makes you to feel comfortable that if you are asked to design by LRFD also can be designed without any trouble, because ultimately you are going to come back after calculating the nominal capacity, either you will multiply by material factor or divide by the allowable stress factor, which will give you the design capacity or will be giving you the allowable capacity. The remainder is the procedure is same. So, that is the idea behind. So, you could expect problems both in terms of LRFD or in terms of ASD. So, because we also have introduced the differences in the previous sessions, what difference it makes with respect to LRFD and ASD. So, by doing this exercise by this time, I think you should be having enough knowledge and idea to solve any problem given to LRFD side. So, in here we have got a UDL distributed load of 500 and a lateral load applied perpendicular to the beam web of another 500 point load. So, you can see here we are going to get a in plane bending for sure. This UDL will create the major axis bending. This 500 kilonewton is going to create a minor axis bending. Of course, there is no axial load. So, you could substitute the equations from what we have learned, and what I have asked you to find out is the combined effect of the in major axis minor axis bending. So, simply going through the parameters, of course, K factors is given as 1 for you already, and unbraced length has been given as half the beam length, somewhere I have specified, somewhere restrained from rotation, the span of the beam is 5 meter and it is laterally restrained at the mid span. So, just like what I have shown you a picture yesterday, that along the mid span here another member is coming and joining perpendicular to the length of the member, so that it does not allow you to rotate about its axis. So, that is the idea behind. So, just substitute the parameters and try to calculate all the other factors you must be knowing, E value, G value, and basically the yield strength value also is given, safety factors for axial bending and shear, and the applied moments you have to calculate. So, basically use this loading and you can calculate the bending moment diagram, which you should be knowing. If it is a fixed beam, if it is a simply supported beam, you should be able to calculate the bending moments corresponding to, and that I have done here. In fact, the tension value, axial tension value is also given, an axial load of 1000 kilonewton is applied at the mid span, so that you can also have an interaction how it is working. And here we are just checking the compactness of the web and the flanges. So, you can see here both the flange as well as the web is compact just for convenience, but you do not think that you will get the same thing, because in any case all the complicated formulas will be given to you as the reference for exam purpose. This is the moment of inertia and section modulus calculations, which is easy to remember, but you can also not remember this large formula, you can just do it from the basics, which is radius of gyration, polar moment of inertia, or torsional constant we call it. So, you should also remember how do we do it. It is basically width times the thickness cube divided by 3 and cumulative of all the segments. Suppose if you have 2 flanges, 1 web. So, you see here how we have done the polar constant is basically P T cube by 3 plus the web is the other way, H T web cube by 3, and cumulatively add, that will give you the torsional constant and the distance between. So, all these are geometric parameters. Then we have reviewed yesterday these axial stress calculations, and in this case is tension, and basically the unity check ratio P divided by P A. Similarly, for flexure in plane bending, and yesterday we reviewed the buckling parameter is LB is 2.5 meter. So, you calculate LR and then LP and find out which category of allowable stress. So, automatically you calculate the FC value, calculate the moment capacity, and then the unity check is so much. Similarly, the out of plane bending, we have got the moment acting perpendicular that to the web, and you have got yielding or lateral torsional buckling, and similar you will find out the capacity. Then you will just decide which formula to use. This is being a symmetric section, we try to use this formula which we learned about today, and basically it is a 70% utilization of the total beam. So, you got axial tension, you also have in plane bending, you also have out of plane bending. So, I think it is a simple procedure, exactly similar like tubular members, only the equations and the idea behind and the parameters involved is slightly different. And the shear capacity, which just we did it in the morning, basic idea is the calculation of CV corresponding to the stiffener effect, and otherwise you will get the CV equal to 1, and basically find out the capacity nominal, capacity allowable, and shear capacity unity check is the ratio of the applied load. So, shear also you should calculate from the applied load. So, what we have done is we have in summary able to understand the differences, because even though the procedure is similar, only the difference between the tubulars and the non-tubulars. Now, we will just quickly look at, before we finish the class today, the connections, what are the differences, so that you could possibly design it without much difficulty. So, there are several types of connections. One is the beam connections, the next one is the beam column connections, and then the hybrid connections, because since the superstructure we may have beams, girders or pipes, because sometimes we do use pipe sections for columns. So, when the beam is coming and trying to connect to the column, which can be a I beam, which also can be a tubular section. So, we just need to just see how it can be connected and how the calculations can be made, that is the idea behind. You can connect it by drawing, but then the resolution of forces and how we make a design. Unfortunately, none of these will be available in any of the codes, because they leave it to the professional engineer to decide what type of load distribution you want to make. So, none of the codes, neither API or the ASC, will give you idea how you will resolute the forces to design it. Like the procedure for tubular connections, we had an elaborate procedure in API, isn't it? Something like that will not be available. So, we need to justify ourselves how we want to deal with it. So, let us quickly look at the configurations first. Basically, a beam connection, one beam is going and perpendicular, another beam is trying to connect like this. So, you could see here there are two flanges, the flange to flange connection and the web to web connection. So, normally what we do is we just you have to remove this portion of the flange and just come and insert, and you will have a welding all along the interface between the web and the flange and web and something like this, and then also there will be a connection between two flanges of the beams. Now, when you apply a vertical load, which is coming as a shear and also a moment. So, you could see here how it will actually develop. Shear will go as a perpendicular member to the web as a shear. Of course, you have a redundant welding here, that will not be too effective, because most of the load will be taken by the vertical weld, which is very stiff compared to the top and bottom weld. Whereas, when you look at the bending moment, you will be able to decouple, which is basically the fundamental idea of decoupling the moments between the strong points. See, the top and bottom you have large web flange area. So, that is where it will get decoupled. So, you will convert as a axial load at the top and bottom tension and compression couple. So, this is where you will find that the welding between flanges have to be stronger enough to take this couple load, otherwise what will happen? It will just come away. So, that is basically the idea behind how you can decouple a force when you are applied as a moment from a incoming member. So, this basically called moment connection, because we are able to decouple this moment into axial force on the top and bottom flange and transmit to the parent girder. Now, what really happens if this I beam which is receiving these two couple forces is too small, then it will introduce a larger torsion which will make the beam to fail, unless you have some other connection going here on the back side to keep this one from balancing. So, you need to make sure that such loads are designed, such loads are taken and designed, so that the beam receiving these loads are able to survive, otherwise it will fail by torsion, and normally this type of torsion supposed to be avoided. So, how do we avoid this? Simple idea is, you go here, where is that? By taking this same connection, I think the sketch is missing. Instead of doing this connection, you just remove this welding and remove this welding. So, what will happen? There will not be any decoupling happening, because there is no receiving flange here. So, only shear will be able to take. So, you cannot apply the moment here. That means, the beam, the beam shown in yellow color needs to be designed using a simply supported boundary conditions, like you will be using WL square by 4 instead of WL square by 8. instead of a big fixed beam which is WL square by 12 or 24 something like this. So, basically either you design this beam for the torsion that is going to come, or you just do not do this welding to avoid these couple forces, but then you design this beam for an increased bending moment, because once you assume or once you have a simply supported condition, your bending moment for this member will be larger. So, you will make the beam stronger enough. So, that may be called a simple shear connections, which is in a slightly different form I have given. So, this is beam connection is just purposely made moment connections. You can also have unequal depth, but of course, then it does a bigger enough damage at some location along the web. So, you may actually have to stiffen this side, so that this web is able to take this force coming from the decoupling effect. Otherwise, you will see the larger bending here, and by that the web will fail. So, the equal and unequal, the only difference is the web local buckling needs to be taken into account. The next one is the beam column. Instead of beam you have a beam column, very commonly used in industrial buildings, in onshore structures, also buildings, sometimes prefabricated buildings, people use this type of connections very often. And basically you can see here the web of this and web of this is aligned in the similar line, so that you do not get buckling, number one, and the bending effects is transferred to the parent column by means of a decoupling effect, which needs to be taken and transferred to the web. See, ultimately the web has to take, that means this stiffener shown in red color is going to prevent the flange from buckling and bending. Otherwise, what will happen? When the force is transferred, this flange will start rotating. So, unless you connect the two flanges by this stiffener and make sure that the load is transferred to the web because of shear. So, that is the idea behind. So, you need to design these stiffeners, which you can make a simple basic mechanics calculation by transferring shear. So, you can take the 50 or 40% of the stress each stiffener will be able to take. Simple connection, how do we make a simple connection? Is very simple, basically the moment is not taken. So, that means you will not bring the flange to weld it towards here. So, only shear can be transferred, because you will not be able to decouple, because there is absolutely no flange to decouple, flanges are removed. So, what we normally do is you remove the flange in the near vicinity of the connection, so that only can transfer shear. So, in this case what will happen, the design of this beam have to be taken into account the corresponding boundary condition, which is basically a simply supported condition, and that means this beam will become slightly bigger. Instead of WL square by 8, you WL square by 12, you will take WL square by 8, because it is supposed to be a boundary condition corresponding to simply supported. So, that is the price that you are paying for, but then you do not need to really stiffen anything here, because there is no bending transferred as a coupled reaction, which that means I do not need to really stiffen here. So, which is alternatively easier for fabrication. Many times people prefer this, but of course, there is a price to be paid for. So, the next connections is basically the hybrid connections, three types. One is circular column, but incoming I beam. How do we do this connection? Second one, I think beam is a I beam section, but the incoming brace is a circular section, which is also very common in topside structures. The third one is a inclined brace. So, you will see that all three of them have little bit difficulty in designing, especially when you take the first one. You see here you have a column and we have an I beam coming in, it is not easy to connect. What we need is basically to avoid a local buckling of the pipe, because the loads are going to come so much concentrated. When you apply a moment, what happens? Such an axial force will make pulling of the tube across the section, which I think we were looking at during our tubular connection design. Such a stress is not so good, because it is going to create local stresses, which will make the pipe to fail by buckling, and that is why we need to distribute the load all around by making a horizontal stiffening ring. So, the load will go as a shear transfer between the pipe and the stiffener. So, by doing this kind of stiffening, we avoid the local effects, but of course, sometimes we also do inside stiffening, because that will make sure that there is no local effects, but then all depends on the diameter of the pipe. If the diameter is too small, you will not be able to go inside and do this stiffening effect. Normally we try to do it outside, but if it is larger diameter, you could also do an internal stiffening, which could look very neat, because nothing is projecting outside. So, sometimes people prefer that. So, in any case, how do we do this design? That is the main thing. The shear transfer is very easy, because you can find out what is the height of the web and multiplied by 0.6 times your thickness will give you the shear force transfer. Whereas, the moment transfer, you need to decouple these forces into such type of point loads and design this ring. This ring can be designed using closed form solutions. I think if you look at some of the textbooks, you will be able to get the beams curved in nature. I think you might also have studied in your applied mechanics curved beams. So, you can just take the load and apply and find out, like very similar to arch, only here is a double arch closed section. So, you can design the ring, and then allowable stresses can be taken as 60% or 70%, and then these ring needs to transfer the forces by means of a circumferential shear along the pipe section. So, that is how you will have to make this design, and this is very commonly adapted in offshore topside structures, very common, without which we can't design any connections, because most of the topside structures, columns are pipes, beams are I sections, and you will see that many times you will encounter this. So, that is why I just call them hybrid connections. The second type is exactly opposite. The receiving member is a I section, which is also common, because in the floor beams may be requiring a middle support. So, at that time you will have a column coming and supporting it. So, in here is exactly reverse problem. The member coming and connecting is a pipe section carrying axial load or bending moment, needs to transfer this load to the web of this section, so that it can go to the neighboring support. So, in here we have a slightly complicated problem. So, you can see here in the plan view, you have a circular section shown in red color, delivering forces on the flange of the beam. Unless you have these flanges are stiffened, supported sufficient enough, the flange will fail by local buckling, which is what is supposed to be prevented. Otherwise, the beam will also fail. Once the flange fails, will not have adequate capacity to even receive these axial forces. So, what we need to do is decouple the forces into axial loads on the yellow color stiffening effects given there, and design them as a short column as per the procedure what we have studied just now. The third one is also similar effect, but only thing is the brace is slightly inclined. So, of course, some component, the horizontal component will go alongside axial load on this member. The vertical component of the P will come and act as a point load on these stiffening effects. Only thing is the position of stiffeners needs to be aligned properly. Do not put the stiffeners outside, you need to keep the stiffeners within the periphery of the intersections. The idea of this, the dot points or the hard point what I have given, because that is where the load will just start jumping, because that is the stiffener location crossing the pipe location, that is where the stiffness is higher. So, if you imagine you take about this point, there is no stiffener at the point below. So, load will not transfer, because the relative to this point is weaker, this point is stronger. So, that is the point of intersection. So, if you keep the stiffener outside, there is no use, still it has to travel through the flange by making the flange to bend, then only it will go to the stiffener. So, if you keep the stiffener inside, the hard points will take the loads sufficiently directly. So, the last one is the similar, only thing is the brace is inclined, but here the axial load will be taken as a horizontal load and vertical load depending on the angle. You can resolute the forces. The horizontal load will go as a horizontal shear to the beam, and the vertical load will go through the stiffeners. Ultimately, the stiffeners will carry the load to where? It has to go back to the web only, because the web carries the shear and take to the supports.